we did first. Okay, so first we did three body diagrams. Okay, and then we also drew shear force diagram and bending moment diagram. Okay, what these thing gave us was V and M. Right? V is the shear force, M is the moment. So from there, now this is the section we're going to talk about is shear normal stress and shear stress. Okay, so this is essentially sigma and tau. And then the last ingredient is there's more circle. Or stress transformation. Maybe I should write here sigma x, sigma y, tau xy. So this one gives us sigma 1 or sigma A, sigma B, sigma C, from which I can get sigma 1, sigma 2, sigma 1 greater than sigma 2 greater than sigma 3. And then final step is design, which is based on maximum normal stress or maximum shear stress. So maximum normal stress is, it could either be sigma 1. So sigma 1 could be tension or compression, but usually we think of this one stress which is tension, so that's going to matter. Or it could be based on sigma 3, which could potentially be a compressive strength. And so sometimes we deal with things which fail in compression, like in civil applications, compression is very important. And then the maximum shear stress, we have the formula is tau equals sigma 1 minus sigma 3 divided by 2. Okay, so we have so far done this part. Okay, we've also seen more circle. Okay, so now what we're going to try to do is we're trying to connect V and M with this. How can we find sigma x, sigma y, tau x, and of course sigma z, and so on, given V and M? This is next part. Okay, and then this will come later in the course. So we are sort of doing design in bits and pieces. We did 1 and 3, and now we're moving to 2. And that is also probably a review for you. This is using beam bending theory and shear stress theory to figure out what those stresses are. Okay, so we'll do 2, and then after we know 2, I think we get the whole picture about how to compute stresses. We'll go to number 4. Okay, so let's get to this part now, which is computing sigma x, sigma y, tau xy. Okay, I'll introduce this and we'll run out of time. So I'll just introduce this and then we'll continue on Monday. Okay, so this part is on how do we compute the normal stresses in a beam. Okay, so assume there's a beam. And then it's subject to a moment m. If it is subject to pure bending moment, which is sort of trying to curl it in a shape of an arc, something like this. So what's happening here is there is a moment m, and that causes the beam to bend.
So I have a good question. When
Yeah.
is this when it's bending, are we providing a load from the top, or we just like how I can in my like picture this like how it's bending like that.
So here we are just looking at something which is subject to pure bending. There's no shear force. But this, what I'm going to do, applies to any beam where there is bending moment as well as shear force, as we'll see later. So I'll actually give an example of how you can get M by applying a force. I'll just show it in a bit. Let me just finish this and I'll show you an example.
Got it. Thank you.
Yeah. So once you do this, you will notice that the top portion of the beam is under compression, or its length is decreased. The bottom portion of the beam is uh, under tension because its length has increased. So this part is in compression, and this is in tension. Okay. How do we get that? Well, if the length decreases, then its stress is going to be negative, and then if length increases, its length is increasing, then stress is positive, which means it's under tension. Okay, so there is this layer. So there's a layer somewhere in the middle, which is not stretched or compressed, right? You cannot go from positive elongation to negative elongation unless you go through a point where the elongation is zero. So this line, there is no elongation, which means there is no stress because strain is zero or elongation is zero. And this layer is known as the neutral axis. Okay, so one question was, how to get pure bending in a beam? Okay, so there is this kind of famous setup which is used by people to do these experiments called a 4-point bending specimen, where assume that one end is on a roller, one joint is pinned, and then you apply two equal forces in the downward direction. E, E. So given this setup, you can draw the shear force diagram. Okay, so it turns out that you can write the reaction forces, but if this distance from where the P is applied to the left side is the same as the distance the load P on the right side is applied. So let me just put that L and L to be the same thing. This is L and this is L. So provided these are the same, you will see that the reaction force on the left side is P upwards and it's P downwards. So then the shear force diagram will look something like this. Positive, it will be zero all the way, it will be negative. P and minus P. And then if you look at the bending moment diagram, which you can find out by writing the equations, it'll actually be something like this. This is P times L. And this is the bending moment diagram. So right here, we have M is P times L, which is a constant. And then from this, you can see that the shear force is 0. So that's an example of a place where that part of the beam, there's only bending, there is no shear force. And that's sort of how you can generate pure bending, no shear force on the specimen. This is actually a famous, it's a widely used way of loading. It's called a 4-point bending specimen. It's often used to apply a uniform moment M, and then you can do experiments in order to put a normal stress on the beam, which by the way, I'll cover next time. So assume that the beam bends like so. Okay, this is really exaggerated, but just for the derivation. What we do is, maybe I should have bent it a little bit more. This way. Okay, so clearly if it bends, you can extend the edges, and those edges intersect at a point, which is the center of some circle there. And let's say that the radius of this circle is capital R, okay, which is clearly depends on how much you bend this specimen. And then let's say that the angle made by the specimen with the loaded specimen with respect to the center is theta. Okay, so let's name a few things. Called the CT. So let's call it C prime D prime to distinguish it from this specimen. Yeah. No, that's a new axis. That's just a section, which I'll show again in a new figure. Hold on. So I'm drawing this same beam without a bending load M, just for reference. And let's draw the neutral axis, which is approximately the middle of the beam. And then I'm going to consider some section away from the neutral axis. Let's call it CT. And so when you apply the moment M, CD will be an arc, C prime, D prime. So if I want to find the strain, then the definition of strain is change in length divided by the original length. So I'm interested in finding how CD changes as you apply the load M. So the new length of CD is C prime, D prime. The original length is CD. And the original length again is CD. So that's the definition of strain. If you like, you can call this delta X. Okay. So note that the entire beam is of length delta x, and because the neutral axis, let's call that A, this point, let's call it A, this point is B. Because that neutral axis doesn't change its length, it's still going to be A and B. It's unchanged, while CD is changed because it's going to be curved. So what we notice is that delta x is the length of CD, right? But also the length of AB, which I've shown here, as well as here, it's the same length. But from that, the first figure, we can write it in terms of R and theta. The arc length is R times theta, right? Arc length. This is the arc length formula. The easy way to check that is, if you want to find the circumference of the circle, you just put theta equals 2 pi, that gives you the circumference, right? So that formula holds true for that case. Now let's try to write C prime D prime. Okay, for that, what I'm going to do is I'm going to consider that this distance is y. So the distance between the neutral layer and the layer I just considered. Okay, now you can see that if you want to find C prime D prime, it's going to be the radius from, well, it's going to be from this point all the way to C prime D prime. That's the radius is R plus y, right? Let me show it here too. This is y, and so it's going to be R plus y times theta. All this 1, 2. So I substitute 1 and 2. The strain is C prime D prime, which is R plus y theta, minus CD, which is R theta, divided by CD, which is R theta. So you can see that comes out to be y divided by R. So strain is simply the distance of that section CD from the neutral axis divided by the radius so down E equals y divided by R. From the previous page, sigma equals strain can also be written as sigma divided by E. What is sigma? Sigma is the stress, and we'll come to the normal stress in just a bit. Okay, it's the stress which, so remember when you take the specimen, you load it, it curves, and I told you that the layer above the neutral axis is going to be under compression. The best way to show that is something like this. And then the layer below the neutral axis is under tension. Zoom this, it looks like this. The layer below is going to be top layer is under compression because the length of the top layer decreases. So the strain is negative, and so stress is negative. This is sigma, very negative, and then this is plus sigma. So that's the stress which I wrote down there. Okay, so now we can equate the two. So we have sigma divided by E equals Y divided by R. And so we can write a formula for sigma. It is E times E divided by R times. Okay, so this formula is telling us something which I think is very important, which is that stress is proportional to Y. In other words, the further away from the neutral axis, the stress would be greater than closer to the neutral axis. And that's why I showed this line. The stress has a bigger arrow on the top than the one which is closer to the neutral axis. So the stress increases linearly from the neutral axis. So in a beam, the maximum stresses will be at the normal stresses would be at the edges, and not so, and will decrease linearly as you go towards the middle of the beam. So max at the extremes and 0 on the neutral axis. Okay, that's the thing. Okay, now we found stress. Let's try to do a few more things with this equation. We'll try to derive a formula for the net force. So we have a cross section of the beam. That's the neutral axis. I showed the stress. So if you want to find the force, then what you need to do is consider the stress on a small element dA. So dF is equal to stress times dA, right? Definition of stress is force per unit area. So the force is delta F, area is delta A, and of course the force is in this direction, as same direction as stress. So now if you want to, so that's the force on a small element of the beam. And if you want to find the force on the complete cross section of the beam, then we need to integrate that expression over the complete area. So the net force equals integral sigma delta A, but sigma delta A is, let's call this 3. Is Okay, so remember I drew this figure of the stress, max stress decreased into 0 in the middle. So now the main observation we make is that if you integrate the stress, or say integrate the force over the whole cross section, some part of that is the top of the beam is under compression, the bottom of the beam is under tension, and the net force in the beam is actually 0, right? There's no force, actual force pulling the beam because it's only subject to a pure bending moment. So this integral here is actually 0. No force in the x direction. Okay, but E and R are constants. And so we can say that integral y dA equal to 0. And if you recognize this formula, but if you have integral of the distance times delta A equals 0, and that's actually the formula for the centroid of the section, right? It's saying that the centroid of the section is the neutral axis. So recap, centroid equals y. You might have seen this formula though, y dA divided by integral dA, right? But what's integral dA? That's a constant. So this term is equal to 0. So it's saying that centroid is at 0, and hence the centroid is the neutral axis. Okay, what's the implication of this? Well, if you're given a regular geometry like a rectangle, you know that the centroid is the half of the length or half of the height of the section. But what if you're given some very complex geometry like a T shape? Then it's less clear where the neutral axis would be. So what you need to do is essentially find the centroid of that cross section. That's where the neutral axis will be located. So this is so. In other words, if I give you this geometry, and then tell you that's the height, then you will easily say that the neutral axis is right in the middle, because that's the geometric center, right? But now if I give you this section, and this section is now subject to a bending moment, right? It is a T section. Now the question is, where is the neutral axis? What you'll do is you'll find the centroid using that formula. The centroid formula is integral y dA divided by dA, and then that centroid is the neutral axis. So compute the centroid, which is y dA. And then that is your neutral axis. And so we'll do a problem where you will be computing the neutral axis for a non-regular shape, like a T section. Okay, an I section is nice because it's right in the middle, but for something which is not symmetric about the horizontal, it's really hard to figure out the neutral axis, but you can do it to the center. So that's why this kind of derivation is important. Now you know how it comes. Okay, the next we'll do is we'll find the moment, right? We found the force by doing the integral of sigma dA. Let's find the moment. the same thing, there is a neutral axis. We consider a small area, either above or below the neutral axis. That one is subjected to a stress. The bottom one will be subjected to a tensile stress, assuming that the bending moment moves the beam in a convex shape, like I showed earlier. Say that this is dA. And then the distance of this layer from the neutral axis, we had called that y. Okay, so let's write the moment. And when you're taking the moments here, we'll take the moments about neutral axis. So that would be TF times y but dF is sigma TA. But then we wrote down expression for sigma. Sigma is E divided by R times Y. A. And so we can plug out, remove the E divided by R from the integral, because E is a constant, radius of curvature is constant once you fix the moment. So E integral y square dA. Okay, and remember that this all is, well, this is subjected to a moment m, so that should be equal to m. Okay, now I don't know if you recognize y square dA, but y square dA is again something you might have picked up in a previous course. It's actually known as the moment of inertia. So this term is called the moment of inertia. So we write this as m equals E divided by R times I. And so also from the previous pages, I wrote down a formula for sigma. Remember, sigma was divided by times y. And so we'll combine all these things into a single formula. Okay, so you don't have to remember those two expressions, but it's much easier to keep track of this one. M divided by I, so I divide this expression by I, you get E divided by R. This is just from first one. But then E divided by R is also sigma divided by Y. We take this. And so the one which I think is very common in bending equations is this formula. So that's the formula we're after. M divided by I equals E divided by R equals sigma divided by Y. And the fact that the neutral axis passes through the center. So I divided by Y is also known as the section modulus. So sometimes in problems, you're given, or if you look at the appendix, which I was just pulled out earlier, you will be given the section modulus, which means that I divided by Y is given to you, and then you can just use that to solve problems. Field bar of 0.8 times 2.5 inch is subjected to a moment m as shown. Find m that causes a bar to yield, and given sigma yield is 36 KSI. This is sigma y is 36. So KSI, this unit means kilo pound square inch. So the system we're using here is IPS. Okay, so we are asked to find M. Yeah, sure. Yeah. What's that? Oh, yeah. In this case, you're actually given sigma y. So this is actually, I should have written this as sigma y equals that. I did not have an editor, but if you editor write the equations as sigma y, but if you're told, you're usually given sigma y is whatever, or the yield strength is whatever. So if you, either of those qualify. So yield strength is 36 KSI. That's the other thing you might be given. If you're not given the equation, then you should look out for the word yield strength. That's sigma y. Okay, so the question is, how is M related to sigma y in case of moment M, right? So the only equation we know so far is M divided by I equals E divided by R equals sigma divided by Y. Okay, so it seems, well, we're not interested, we're not given Young's modulus E. We don't know the radius of curvature R. So we just use the, so there are two equations sitting in there, right? You could equate the first part to the middle one to the end one, or you could equate the first part to the third one. It's not three, but two equations, because there are two equal signs. So what we'll do is we'll use this equation, M divided by I equals sigma divided by Y. And so from this, we can find M, it's sigma I divided by Y. Okay, sigma is the stress, I is the inertia, Y is the distance from the neutral axis. Now, in this case, since this is a very regular geometry, the neutral axis passes the center of the beam. This is neutral axis. This distance is Y. There are a few things we need to understand here. That is, if this bar, which is subjected to pure bending moment, will fail, the point at which it will fail is where the stress is the maximum. And the stress is maximum when the distance from the neutral axis is maximum. So before this part fails, this part will, the plane which is furthest away from the neutral axis will fail first, which means that either this part will fail or this part will fail. Here the stress is compressive, here the stress is tensile. So, you know, these materials either have the same yield strength in tension and compression. If they're the same yield strength in tension and compression, either of those two will fail at the same time. Most times the strength in tension is less than the strength in compression, in which case the bottom half will fail first in the top part. Okay, here, since you're not given anything about that particular property, that which is you're not given if it's the compressive yield strength or the tensile yield strength. So we just assume that the tensile strength is the same as the compressive strength equals sigma y. And so the top part and the bottom part will fail first. Okay, and so we'll use that here. So we'll say sigma is sigma y, because they said that's going to have the highest stress. Secondly, the y is the maximum of the distance from the neutral axis. The maximum distance is going to be half of this 2.5. This is 1.25. Let's call that, like, let's call this B. Let's call this H. So it's H divided by 2. Okay, the last piece is the inertia. And for the inertia, actually, if you need to go back, by the way, it will be given to you, but if you want to find it in the book, the appendix has a table which has all these section modulus for different shapes. Let's try to, I think it's A18, but I may be wrong. Let's see what's an A18. 1044. Yeah, this is the one. So here, this is a rectangle, circle. It basically gives you Ix, Iy, and I, and Jg. J is the polar moment, I is the moment of inertia. I think this is the geometry we are after. Our axes are along the x-axis. So we are looking for Ix. It's BH cube divided by 12. This formula. You see that, BH cube divided by 12. If you, so this is applying a moment this way. So if you turn it and apply it this way, then your x becomes y, and then you use the other formula. So you could keep it like this, apply this moment, or you could keep it the same way and apply the moment the other way. Then it would be. The moment is, okay, so let me just draw that here. So when you talk about this beam, neutral axis is this. The moment is like this. When you say this moment is this fashion, what you really are doing is, so this is the z-axis, the x, the y. This moment is about the z-axis. So the way you do it is, you take your right hand, you point your thumb towards the z-axis, and your fingers gives the direction of the moment along the z-axis. So when you have mz in that fashion, then what you do is your formula is P H I would be PH cube divided by 12. So if you want to change the problem to reversing it, then what you would do is, so in that case, the moment would be this way in y. So I think that will be confusing here separately, but that would be the moment. So here we can write PH cube divided by 12. So 36 2.5 divided by 2. We wrote B as 0.8. Times 2.5 cube. So M, after plugging in the values, comes out to be 30. And if you are talking about IPS unit, it's kip inch